We've been thinking about how fast reactions run. We've thought about how concentration or temperature impact reaction rate. In this lesson, we'll start to understand why temperature specifically impacts the rate of a reaction. To do this, we'll think carefully about the energy of a reactant as it becomes a product. When we understand these energy diagrams, as they're called, it helps us understand all sorts of things about a chemical reaction and its rate. Let's take a look. In this lesson, we'll introduce reaction energy diagrams. Then we'll define key terms in energy diagrams. And lastly, we'll practice using energy diagrams so you become really comfortable with them. First, what's an energy diagram? Well, it just tracks the energy of a reaction over time. And so on the y-axis, that's our vertical axis, we have energy. And as we go up, that means we're going to be increasing the energy of our reactants or products. And as we go down, that means we'll be decreasing the energy of our reactants or products. We're tracking this across time. And so our x-axis is extent of reaction, meaning how far has it gone towards products. And as we move from reactants to products, we're just thinking about going forward in time, getting closer and closer to those products. In this video, we will track this chemical reaction where we're taking carbon monoxide and combining it with O2. What's basically going to happen in this reaction is one of my oxygen atoms is going to go over and hop onto that carbon. And when that happens, I'm going to make CO2 and I'm going to make just one oxygen that's left over, one oxygen atom left by itself. Now, what we can already tell from this energy diagram is that our reactants right here are higher in energy than our products. So we're ultimately going to be going downhill. As we'll come to see, that turns out to be called exothermic. But even though we're going downhill, we're going to see that our molecules go through an uncomfortable in-between state. That to get to products, they're going to have to actually go up in energy to a big, nice peak and then way back down. Okay, why is that? Well, that's because change is hard. Change is hard for people. So if you're moving to a new town, or you're starting at a new school, or you're changing jobs, there's these weird in-between periods where you haven't gone to the new school yet. The new house doesn't feel like home, or you've quit one job and haven't started another. And in that in-between stage, it's uncomfortable. And that's true for molecules as well. So in this chemical reaction, when they're in between reactants and products, that's when they're actually the highest in energy. And we call that the transition state. So the transition state is the point of highest energy during a reaction. For this reaction, it's right here. And notice we've shown that this is when carbon monoxide, that's CO, and O2 are colliding. So they collide and they begin to form new bonds. So maybe this oxygen and that carbon begin to bond together, and the oxygen bond right here between this guy and this guy starts to break. Well, that's what we need to do to go forward to our products, but it's actually a really unstable in-between state called the transition state. And so molecules have unstable bonding in between reactants and products in the transition state. And that's what makes them so high in energy. They have to get uncomfortable before they can get more comfortable. Now, how tall this peak is called the activation energy. And we symbolize that with E and then a little a. So this stands for activation energy. And activation energy is the energy required to take the reactants to the transition state. So we start down here with reactants and we want to go all the way up to the transition state. And that requires energy. So the activation energy is the energy required to take the reactants to the transition state. And it turns out that we reach the transition state more likely if we're at higher temperatures. So reaching the transition state is more likely at higher temperatures. And that's actually another reason why increasing temperature increases the rate of reactions. Remember, we said in a previous lesson that if I increase temperature, then I just get more collisions. And that's true. Molecules are bouncing all over the place and they collide more often. But increasing the temperature also means those collisions are occurring at faster speeds with more energy and are more likely to give them enough energy to get to that peak. Okay, so that's activation energy. The next term you need to be familiar with is enthalpy, and that's the heat released or absorbed by a chemical reaction. So here we actually don't care about how tall this peak is. We only care about the difference between our reactants and our products, because ultimately the amount of energy we get out depends only on this difference, enthalpy, which is symbolized with delta H. So if the reactants are higher in energy than the products, we call that an exothermic reaction. It's going to release heat. And so we can actually look at an energy diagram and determine if it's a chemical reaction that will take heat or give off heat. So we can divide our reactions into two categories. Either endothermic, which are reactions that take energy, or exothermic, which are reactions that release energy or heat. And if I look at my energy diagrams, I can figure out which one's which. So on the left, we see here that the energy of the reactants starts out higher than the energy of the products. Ultimately, that means my reactants are getting more stable and they're going to release energy into the surroundings. So on the left here, we're going to have our exothermic reaction. So this one is exothermic. And notice that if I think about the sign of delta H, it's dropped. And so exothermic reactions, like we learned before, always have a negative enthalpy. There's a decrease in the energy there of our reactants as they go to products, and that energy is released into its surroundings as heat. On the other hand, on the right-hand side, our reactants start here, and then they have to go uphill, ultimately, to get to their products. And so that's going to be an endothermic reaction. So on the left here, we have an exothermic, and on the right, we have an endothermic. And just like we saw on the left, we can figure out the sign of enthalpy. Ultimately, delta H here has to be positive because it went up. And so delta H here will be positive, just like we learned for our endothermic reactions before. Okay, so energy diagrams do a really good job of comparing these endothermic and exothermic reactions. Now let's go ahead and practice thinking about chemical reactions with this question. Go ahead and pause the video and see if you can answer them yourself. This question asks, is the reaction endothermic or exothermic? There, all we have to do is compare the reactant side, which is here, to the product side, which is here. We notice that we drop in energy. And since we drop in energy, that makes it an exothermic reaction. The second question says, estimate the change in enthalpy, or delta H. So all we're going to do here is we're going to look at the energy for our reactants, which is about 10 kilojoules, and compare that to the energy for our products, which is about 5 kilojoules. That means it drops by 5 kilojoules. And so our enthalpy is going to be -5. So delta H here will be -5, and the units will be kilojoules. Notice, because the products dropped in energy, we have a negative sign for our enthalpy, which is consistent with the answer to the first question, telling us that the reaction is exothermic. Okay, next let's ask, what is the activation energy? How much is the activation energy? So again, we just need to take a look at the energy for our reactants, which is right there, about 10 kilojoules. And then we compare that to the transition state, which remember is right here. And so that transition state occurs at about 35 kilojoules. So we go from 10 kilojoules all the way up to 35. So that's an increase of 25 kilojoules. And that's what we'd estimate for our activation energy, that our activation energy would be 25 kilojoules. In this lesson, we've introduced reaction energy diagrams, we've defined key terms in our energy diagrams, and we've practiced using these energy diagrams.
Hey, hey.